We're going to do a crash course lightning talk on ZFS and Postgres. And most of these things are applicable to not just Postgres. Most of what I'm going to talk about is file system related and storage related and how it relates to databases. But you should be using Postgres even though we're at a MySQL conference. So if you're not using ZFS, you're losing data. This is pretty much the most important thing that you can take away from this talk is if you're not using this, you're losing it. And you don't know it, you probably are. Clarke's three laws. Any sufficiently advanced technology indistinguishable from magic. ZFS is magic, but it's not quite magic, but it's impressive software regardless. So there's many things that go into ZFS, and if you follow political, humor, maybe that's too soon, maybe it's not. So in the ZFS world, most everything that you do is most everything that you do, you're used to tuning things. In ZFS blind, you kind of have to do a handful of things that with regards to tuning, but generally speaking, there's not a lot that you need to do. So we're going to go through a handful of things here, and we're going to move through this deck pretty quickly, largely because this talk was originally oriented towards a 50-minute talk, and the talk got shortened because of scheduling down to 25 minutes. So we're going to move fast. So. One of the most important things about databases is the fact that it stores data on disk. So what does it mean to talk about what a database does with regards to its storage of bits on disk? Because that's really what we care about. That's why we use databases. All of your stateful applications end up on disk, as translated through an SQL layer, MySQL, Postgres, Percona, whatever. And at the end of the day, you've got some backing file system or storage organization of storage, and we use ZFS, or I am recommending. So on the storage side of things, when you see a write-ahead request come through, you're going to have the database system issue a write for the write-ahead log or the bin log, whatever, and that's your intent log, and it's going to show up as an 8K page. Fantastic. It's a P-write. It shows up as basically sequential I/O. This is very compressible sequential I/O, but it also gets churned and turned over pretty quickly. Pretty simple workload. This is basically a sequential append operation. Very nice and performs very well in ZFS because ZFS, as we're going to get to, is a log-structured file system. The most important part of databases on ZFS may have to do with data integrity and the ability to move forward and backward in time, and the ability to take snapshots in basically a pauseless way. Taking snapshots on ZFS takes handful of microseconds compared to a normal block storage file system where it actually has to freeze the entire world and walk all of the available inodes, which is a terrible place to be if you're trying to be a 24/7 operation. You don't have an off-duty cycle that you can potentially take a backup. In theory, you should be able to take these kind of backups and do this maybe once a minute, and that should be an okay thing. And in fact, it is when you're using ZFS, and it's not the case with any other file system. So UZFS backups are a fantastic thing. It's very simple. Backup or PG start backup to do the logical flush, and take your snapshot and say stop backup. So that's fine and all, but what you also need to do is you need to go and flush this data to disk. And so what you actually need to do and create a memory coherent snapshot is to take a checksum and flush the data, all your dirty buffers, do a start backup, grab some data, or however you're going to do it, and stop backup. In this particular case, this little random backup utility happens to be ZFS Snap. And at that point in time, you actually maybe can simplify things further and remove that checkpoint and just use your 3 commands. And so you've got a very performant, fast, and reliable backup system that comes in the form from ZFS for regardless of your database, but in this case Postgres, in basically 3 steps. And there's not much that you can't optimize this problem any further. You're always going to have this set of 3 steps. So great. At the end of the day, you figured out how to do efficient Postgres backups. So ZFS and Postgres are both databases. One of them is a database of records. And the other one is a database of blocks on disk. And there's lots and lots and lots of parallels between ZFS and Postgres. Okay. So Postgres is very much copy on write. You've got, as a result, and in Postgres, you've got blocks that are checksummed. ZFS, everything's checksummed. The ability to perform sophisticated maintenance of your information and compress things in a way that is abstracted because you've got good separation of concerns. These are all kind of first-class citizens of when you're using ZFS or some form of log-structured file system. ZFS really being the only option that you have available to you. So let's see. There's lots of different ways that when I was talking about separation of concerns and the ability to have different checksums or different layers and different layers handling different things. On the checksum side of things, you have the ability to abstract from the database the ability, the notion that a particular disk was returning some bad data. So, how do you end up with bad data in a database? There's lots of different ways of dealing with it, of having this problem manifest itself. Parity errors are one of my favorite firmware bugs. All of these are hidden away from you when you're in when you're using some form of file system that has built-in integrity. ZFS has that. Use ZFS. Okay. So, very fast, high-level overview of what ZFS does and why it's kind of useful. But the internals are really the important thing, and understanding the internals lets you use the technology for what it is and incorporate the value add and the feature set that comes from ZFS into the rest of your application design or database design. So if you've got a normal block file system, which is basically the entire Linux ecosystem, you have when you issue a write, you write to a file descriptor, and you take a buffer and you destage that down to disk, and you make this VFS call, and you pass that buffer from userland to kernel, and the VFS layer goes and does a lookup and figures out where that file and that buffer exists on disk, and you write that buffer to disk that's in some offset in a file. Internally, the kernel then maps that buffer to a handful of system buffers, and then under the hood, I wish I had some water. Under the hood, oh, is there? Fantastic, sorry. Under the hood, it's actually taking that buffer and effectively doing like a scatter-gather operation and writing that down to different logical buffers on disk. On disk, these logical buffers then are scattered throughout the platter, and it's the operating system and the file system that actually are responsible for doing the fetching of all of these blocks on disk. And in assuming that the little circle there is actually spinning Rust, and these are your blocks, you can see that when you go into a sequential read of data off disk because you're trying to read some random file, in this case, something out of the global catalog, it's internally doing a bunch of random read operations off disk. But in what you thought as a user was that these were actually like logically ordered blocks, and that's not the case. Okay. So, if you have a write count 2 8K buffer, what that actually means then is that, in detail here, is what we want aligned boundaries. So we have an 8K buffer, and it goes and chops that 8K buffer up into the logical blocks. These are normally 4K, doesn't have to be, but typically 4K, let's say they are, at least. That's kind of the modern standard at this point in time. And internally, it goes and does exactly what we had earlier, where it goes and fans out and writes that data on disk. Okay, fine. This is block file systems 101. Right? This is what's happening when you go from PG data global 1 to some physical storage layer. This is high enough level, but gives you just a taste of the detail there. So when you go to update an individual record or a bit, any bit in a row in any kind of a database, what actually happens? So that tuple inside of a table goes and results in rewrite of the entire buffer. And so one bit here, if you go and change enabled from true to false, let's say, you have to go and make an 8K write, and that's what we call write amplification. So, one of the recommendations that come as a result of using Postgres on ZFS is you can turn off full page writes, because under the hood you're making an 8K write logically, But you don't actually need Postgres to make that entire 8K write again, because the copy on write semantics actually are happening under the hood inside of ZFS, and you can reduce the amount and the size of this write syscall here. So this is an important one from a performance or write performance perspective. So at the end of the day, then, when you make your 8K write and you want to chop and scatter gather that information down to logical blocks, you also care about the order. ZFS provides this ordering guarantee, which means that if you go and have a checksum or checkpoint and you need to replay all of your logs, you can rely on the fact that when your application, in this case Postgres, transits from user to kernel, that the ZIOs or the IO operations that happened to ZFS will come back in order when it goes and does its checkpoint replay. So that works out really well, because now you can guarantee up to file system transaction semantic boundaries that IO operations have happened, and they've happened in a particular order. And that's really important for checkpoint and replay, because you know the order in which things happen, because going back to the wall log from earlier, the intent log, you've already written out a stream of events in sequence, and you can walk that and get this good data guarantee in order to get back to a consistent place. Which is the long way of saying that on ZFS, you don't have to worry about doing database integrity checks, because in the event of a catastrophic failure, your database is going to come back up, you're going to do your checkpoint replay, and you're going to get back to a transaction group boundary whenever that checkpoint restarts or is finished. So on the ZFS side of things now, you can see that a VDEV, so physical side of things, right? One of the things that ZFS does is it has decoupled the logical representation, which is to say a file is decoupled from the actual physical storage. There's no, the block management where bits are actually stored is hidden through, hidden by this device abstraction layer. Okay, great. Which allows us to take mount points, VFS mount points, and abstract them behind dataset attributes inside of ZFS. So, I'm sorry, datasets. So datasets here have independent attributes. These independent attributes you can then mount onto different directories. And this is important from a database perspective, because different directories here, you're going to store different files or different types of files, and those storage characteristics of those different directories are logically grouped. That logical grouping allows you to tune these parameters differently. So what we see then in ZFS, because ZFS is this very large, it's like 500,000 lines of code, it's enormous, complex piece of software, is that IO operations come in from the top, they go through the POSIX layer, they map into this database, the ZDB, the ZFS database. They map through to actual an allocation system and scheme that goes and then does dispatches to the individual disks. This goes back to the original slide that or one of the original slides there, where I said that IO operation, or that ZFS and Postgres are reasonably similar, because they're both copy on write databases effectively. So what does this actually look like? And I apologize, I am trying to move through this to get to some of the best practices here at the end, but some of this hopefully will resonate on some level, is that if you have, back to that update, if you want to go and twiddle a bit on disk, internally ZFS goes and builds this out as a Merkle tree. And so if you have a block that you want to go and make a change on, the change that you make is actually down here on a leaf node, and internally it goes and rewrites this blockchain all the way back to the Uber block, and at which point things are changed. And if this is the way that things, you're walking a B tree, if you do this in a normal block file system, at what point do things become inconsistent in in a log structured file system, at what point do things become inconsistent? And they don't. Right. I have a hidden slide in here, sorry. It doesn't ever become inconsistent because the visibility of the blocks at T1 were never visible, because you actually traverse from top down in this Merkle tree starting at T4. So ZFS as a copy on write allows you to do a bunch of interesting things from a performance perspective. So what actually happens is you make this twiddle, you update a copy of this particular page, and you walk this change all the way up to the top of the Uber block, and at no point in time, because you have consistency at T1, T2, T3, T4, at no point in time were you in a position where your file system was inconsistent. There is no point at which a ZFS file system can be in an inconsistent state. As a result, there is no FSCK. Right? So if you have very large data sets, you never need to file system check. The system bounces, let's say, hardware, data center power loss, kernel crash, doesn't matter. When the operating system comes back up, it can go and get a consistent view of the world. This is from a data structure internals perspective. This particular point is really important, and it allows you to go and leverage some of these kind of like semantics in a way that lets you build an application that's potentially faster than you would normally be able to if you're on a block file system. So again, the answer is never. It's never inconsistent. So actual tips, tricks and tips. So compression ends up working out really, really well for Postgres and MySQL even. So both databases deployed on the petabyte scale, both LZ4, or not even both LZ4. LZ4 is what you should use for all databases, and I will make that statement as a carte blanche recommendation for either MySQL or Postgres. For SSDs or spinning Rust, it doesn't matter. For bin logs and wall data, it doesn't matter. Use compression. It ends up being a net win. We replaced Fusion IO with SSDs using LZ4, and we outperformed Fusion IO. To 2.8 to 1 is not an uncommon compression ratio for Postgres. Across petabytes worth of data, there were cases where this was very good, 100 to 1, and at times we did have, and the background here being a large engineering organization with a bunch of microservices, we had some database instances where they were storing binary data, and it was encrypted binary data, which meant that the compression ratio was garbage. But generally speaking, this was good. Go ahead. Yes, and the reason I do is because LZ4 has a short circuit on its compression, so if it notices that as it's compressing things, it's not getting anywhere, it'll short circuit the compression. So if you were using LZ4, then you do need to manually enable or disable. LZJB, you need to manually. Okay. Yeah, that's exactly it. If you're using LZJB in compression, you do need to manually enable or disable. LZ4 automatically does that for you. Z standard, whenever that shows up, you would automatically do this for you as well. Yes, and really, like, it doesn't matter what your media is, always use some form of compression. Ask me later about why maybe you shouldn't use gzip, but in all other cases, basically rely on LZ4. You can go and query this. This is not uncommon in practice. Don't mix and match LZ4 and gzip on the same box. And because the latency characteristics of the IOs going in and out of the system changes for the worse when you enable gzip 9. You do get better compression out of this, but the kernel wait time for all processes goes through the roof for reasons that actually have not been entirely figured out to date, to the best of my knowledge. So this is an interesting one. When you go in and write things and you're doing this log structured append, because if you go back to where that tree diagram was, all of your writes actually end up showing up as append operations, right? Which means that all writes that happen in the same time boundary end up having locality on disk. Right? Which means that if you go and read some related attribute, it's going to get read off disk at the same time because it's on this potentially it's very probable that it's written on the same 4K page of data because all of those I/O operations ended up on the same page. Right? On a block file system, you may take some nibble and put it off on like block 1 and some other nibble and know it's going to go on block 2. You're going to have to do a random seek, especially on spinning media. In ZFS, those may actually come back and end up on the same physical page. So this ends up being an interesting performance win. If you go and compare that with PG repack, which is the equivalent of like doing I'm going to call it a defrag just to be technology agnostic. But like to do like, some kind of a repack, you can actually go and get very, very both good compression and performance because you have a high degree of locality for related data. Slideware is online later, so you can go and get those links then. I'm more worried about time than anything else, which is, again, why I'm moving really fast. So, yeah, don't ever use dedupe. I know that it's a feature flag. Don't ever, ever, ever do it. There's lots of reasons not to do it. So the reason I came back to slide 1 there was when I made the comment of if you're not using ZFS, you're losing data. This has been studied on reasonably large scale. This was an interesting study done both by CMU but at Facebook of their data set, which is enormous and larger data set than what I was working with at the time. These guys' numbers with regards to uncorrectable errors is in line with what we experienced on a smaller scale. Our smaller scale was on the order of magnitude of petabytes, and we were seeing single to double digit rates of uncorrectable errors on SSD media. Without ZFS, that would have the data would have silently corrupted without our ability to detect. Right? It's not that the errors don't exist on other file systems, it's that you have no way of knowing. With ZFS, you can actually detect that. And not all SSD vendors are created equal. This particular vendor I can name. I know exactly who that is because their error rate was off the charts awful. Amazingly bad. So, This is being recorded. Ask me afterwards. 4.2% to 34%, this is common. This is industry common, right? You probably want to be closer to single digit, but having double digit is actually not uncommon. So if you think about this, uncorrectable bits per year, do the math on this, and all of a sudden you end up in a situation where you're ending up with 99.9% of your servers have at least one piece of bit rot per year, right? You put enough disks in there. And that's kind of scary, right? And that's on metal, right? On cloud providers, they actually abstract some of this from you with EBS, where they actually do their own erasure coding on this. Not erasure coding like S3 erasure coding, but they do their own error correction. And you don't have to deal with this directly. I have seen people send me ZFS scrubs where on Amazon they're actually seeing non-zero error rates coming out of EBS. Kind of go, oh, that's spooky. So things that typically cause uncorrectable bits, temperature bus, who knows what actually contributes to this kind of failure. I am going to move faster. This is what we care about, is the fact that you can do a scrub on ZFS, and it will tell you how much data has been repaired, because as it's walking all of its checksums and verifying its integrity, it'll tell you how much data and number of errors and how long it took in order for something to come back in a failed state. This particular SSD study has been replicated on spinning media and pretty much every other form of storage media out there. And why did I tell you that? And so I can tell you this. I'm going to skip all of the interesting terminology and get to some more interesting bits here about ZFS specifically, which is how do you use it, ZFS create zpool. And you're able to do this directory manipulation and creation of data sets and directories online on the fly. Zpool list, it's very easy, very human friendly, very machine scriptable. This is an important element of command line utilities. Anybody that's designing command line utilities, please take note of specific flags and allow it to be easy to parse input and output. You can set your quotas, you can perform a bunch of interesting things. Tuning tips, disable A time, enable compression, tune your record size, and consider tweaking the primary cache, because databases already have their own userland cache. You don't need to have the file system caching data that you're already going to cache in user space. You don't need to cache it twice. If you go and tweak the data set, and when I say data set, I mean per directory, the ability to tune the caching characteristics of a directory on a per directory basis, change the primary cache to metadata only. It's very easy to go do. ZFS get, you can figure out what the existing parameters are, make your tweaks, go and figure out what it is. It's all done online. It's, takes a couple of seconds. It's very easy to do. We're not going to get into the discussion element of this, but you can change your record size and set it to 16K if you need to, which is interesting because that's a multiple of Postgres' record size. Well, why wouldn't you want to have that aligned? Well, it's because you've got this 2.8 to 1 compression ratio, so I can get 2.81 additional, chunks of data into the same 8K page size on disk. This is interesting in that you can go in and basically prefetch data as a result of using compression with a larger record size. You have to chase that all the way through to the physical layer in order to figure out whether or not that's good or not for your application. Because it's log structured, it's also very fast. You can do huge amounts of throughput quite easily. Where is my... there we go. Right, 228,000 write operations a second. That's the number I was looking for. And this was all done on spinning Rust, right? This one was 16 drives, right? So this is not some enormous SAN, but it is like it's a sizable server. ZFS got your back. Do your scrubs. Make sure that that's automated. It will tell you what to look for. This 0, 0, 0. You're in probably a healthy place. ZFS again tells you this. Other file systems will definitely not. Checksums. This is something that's confusing. When I say this, I'm talking about the amount of storage used per data set. I'm not going to get into why that's confusing, but be aware of that if you're coming into this as somebody who hasn't used it in the past. Backups. This is great. I love doing this at live. This is slideware, but you can go do this. And it turns out that what would normally be a catastrophic operation, RMRF, and Postgres' behavior this when it detects that its entire data set disappeared is actually not that hard to recover from because you just do a rollback. And that's really that simple in order to move forwards and backwards in time. And doing this on gigabytes to terabytes worth of data can take anywhere from seconds to tens of seconds. That's it. And that's really important because you all pretty much never want to be in a position where you're going to point-in-time recovery in order to restore. I would much prefer this. If you've ever had to go through point-in-time recovery procedures, that's awful compared to just running this and restarting Postgres. Cloning is very convenient where you can go in and take a snapshot and mount it in a different place and start up your database and test PG upgrade. And naming conventions of your data sets, which map to individual directories, have some convention there. Don't do that entirely willy-nilly. It works in your favor. You can move data sets between servers. This is really convenient as well. You can do this incrementally or whole data sets, carte blanche. Very, very useful for moving data around. You can take a snapshot, you can send it, you can send this over a pipe, which means that you can send a data set or a directory of data between two different or between two different servers because you did a ZFS send, pipe, SSH. On the other end, you do a ZFS receive. You use root. These are all root operations. No. This is basically a trusted stream of data. That would be nice to have. I don't think that's happening anytime soon. In ZFS? I need to talk to you. Hold on a second. You're not allowed to go anywhere. So then you can do snapshots incrementally. It's very useful. And I'm not going to explain these two slides because I heard that other room clap. Last one, log bias throughput. You probably want that to be your common case. Bypass the ZIL. You don't need the intent log for your common case operations. Maybe for things where you actually do care about data loss up to the transaction group size, which defaults to 5 seconds, you can tune that down to 1 second. Change your log bias to throughput. MySQL has the ability to sync once a second. Turns out if you go and do MySQL syncs once a second, you probably are also very okay with having your log bias equals throughput and setting your ZFS transaction group sync timeout to also 1 second. I'm okay with typically, in most cases, with 1 second of most cases. I don't want somebody to quote me out of context, but most cases, 1 second of data loss if I get a 10 or 100x increase in my write volume. Okay, I get a substantially higher yield out of my database as a result. How do you go and configure some of these things? Again, for the slideware for later on, so if anybody cares. Synchronous commits, similar in many ways, but again, log bias throughput, nice. And we are hiring, I am 1 minute over. Whew. Questions? You're not allowed to leave, though. Robert? James?
So have you actually benchmarked that last one?
Yes. Yes, we did benchmark this. This gentleman over here, Peter, was involved in that. We ended up seeing that transaction group of 1 second outperformed 5 seconds. And I think that it had to do with the number of pages that were in the transaction group that were in the process of being coalesced to disk, which meant that you had fewer number of I/O operations that were potentially pinned behind a lock because the transaction was deserializing. No, because we assumed that Merkle trees worked. James? That was on FreeBSD. Yeah, this was all this demoware was done on FreeBSD. Yeah, and it also works on Illumos, I hear. Oh. Which doesn't work. That's true. Yes. It sorts the dot first. Yeah, which is a clever thing. Yeah. No, this was all done on in this case BSD. ZFS on Linux would have the same semantics. There you go. CentOS as well, and Ubuntu now, which I'm very excited to see. Like these are not BSD or Illumos specific things, but they're definitely first-class citizens in those environments. Linux is getting there. Congratulations. In the meantime, there's other production-ready systems that do this stuff very well. I think we need to wind this session down, and then we can talk more. Because that sounds like a good, interesting conversation. Go ahead.
The rollback.
Yeah.
When you do the rollback.
Yeah.
Is the snapshot is still intact and your main.
Yep. Snapshot has not gone away. Where things get complicated is when you're doing rollbacks on clones. Yeah. So you need to be a little careful with some of that stuff.
The next question is snapshots are free, but how is the clone? When you
Clones are fine. Where you pay the price, the deferred cost in snapshots is in the deletes. Period. Snapshots free. When you go to delete a snapshot, that's where you pay the cost. There's an excellent talk by Kirk McCusick that I would highly recommend going and watching if you are interested. Schedule your deletes for the middle of the night because there is I/O associated with that. And if you don't have a middle of the night, then you should probably be doing this pretty incrementally 24/7 and just accept that as like a steady state part of your workload.
So whatever you're talking, are these increments or?
Oh, definitely. This is 100% of a publicly traded company is running on a very similar setup. Now 100%. MySQL and Postgres. So, yeah, and it's been very valuable to be able to go and run the rollbacks on a per minute basis, or taking snapshots on a per minute basis and then being able to roll back whenever you need to. The mean time to recovery, because you have these once-a-minute snapshots, is very, very valuable when you don't control the behavior of developers that are potentially doing drop databases. That's a different question. I'm not trying to answer it. But as a backstop to the fact that developers do run drop database on a periodic basis for reasons that no DBA could explain, you do need some kind of way of solving that kind of random entropy. So, and ZFS rollback works. If take them once a minute, it's cheap. You do have a cost. Don't let them accumulate forever. But there's a bunch of good scripts that are associated with that.
do you have
ZIL, no. Log bias. ARC, for a second, typically not. Not if you can, right? There's environments where that makes sense, but generally speaking, no. If your primary data set is on SSD, doesn't buy you anything. If you're coming off of spinning Rust and your I/O latency is like 10, 15 milliseconds, let's say, then yeah, it makes sense to go and have an SSD L2 ARC. But yeah, SSDs are getting cheap enough that you could just go that route. Depends on your size of your data. The compression gets you a lot, even on SSDs.
So do you recommend doing different record size for different
No, actually, I totally skipped over this. When I was talking about consistency and naming conventions for data sets, we put both the wall logs and the actual data in the same directory so that you could do a ZFS snap send and get everything back. Coordinating it across across different data sets that idea doesn't fly. So if you go and put an entire database, including its transaction, on the same data set, it works just fine. Then you can snap send and move it. The performance advantage of having your transaction logs off to the side when you're using log bias equals throughput, it goes to 0.
And you also don't use prefetch.
Correct. Yeah, we found prefetch to not be conducive to performance. We found compression to be a win, using the same data set to be a win. 8K performed worse than 16K, which was interesting because it turned out that, and not always, but in the common case, and the reason is we were basically pre-faulting and pre-fetching adjacent pages because there's enough sequential I/O in either indexes or tables to want to pre-fault and preload the next adjacent record into memory.
Now the primary cache out and the block size, record size 128K.
Yeah.
Beat all other configurations we tried with MySQL.
There you go. Yeah, it doesn't surprise me. It's take some of these tunings with a grain of salt because you have to go and test it. And we had different workloads where it ended up being different. But generally speaking, if you had to go and stamp out some defaults, here's some defaults that work pretty well in practice. Yeah, definitely. Do not put any of this stuff behind RAID controller cards. The worst thing you can do, and that is a great set of stories that I can get off the record, is why you don't ever want to use RAID cards. Use HBAs, maybe SAS expanders if you have to, but use HBAs and direct wire your disks if you can. Expose individual disks back to ZFS so that ZFS knows what's going into your R pool or tank or whatever data set, whatever you call it. Mirrored VDEVs works best. So if you have a bunch of mirrored VDEVs, so if you've got 24 disks, you have 12 VDEV mirrors. I did not get into the structure of what a VDEV is. That was in a huge chunk of the deck where I skimmed over that. But you can't ever lose a VDEV, so make sure that you have enough integrity and safety guarantees to never lose a VDEV, because if you do that, the entire Z pool is gone. And I'll go back. But yeah, the gist of it is mirrors work very, very well. Especially on BSD, they had an I/O scheduler that lets you dispatch I/Os to individual devices in the VDEV. So VDEV here. So if in a mirrored case here, if this particular disk is being sluggish, depending on your kernel, it would actually send all of your I/Os to, let's say, to disk 6 because disk 5 is in the process of timing out, which was good from an availability perspective, right? RAID Z, it's fine. It works just fine, and actually performs quite well, much better than you would typically expect. Yeah. Yeah, we actually saw we saw a performance impact, but it's on the order of percentage, not orders of magnitude. So again, log bias throughput, it kind of goes away because you're not waiting for synchronous operations to, let's say, n number of disks. The trade-off, this is a little fuzzy. 5 disks is about kind of the threshold where you move from RAID Z to RAID Z2. So between, let's say, 6 disks and 11 disks, you go and subtract the parity disks, find some power of 2 multiple, and then you want to make that. So if you wanted to have 8 disks and you wanted to RAID 8 disks plus 2 means that you had a VDEV size of 10 disks because your actual data size was 8 disks, right, which is a power of 2. RAID Z3 at 16 disks, which means that it was 16 plus 3, so 19 was the total size of disks that you'd put in your VDEV.
So we did our test when we first set up as the one VDEV, it was horrible. We divided into 3 VDEVs.
Yep.
RAID Z2, and it gets better.
Yes, that very much matches. So we used anywhere from 8 to 12 VDEVs that were mirrored. Yeah. But don't lose both disks. You start to run thin there, or can. So if you know that it's going to take a long time for your operations team to come through data center operations and replace a particular disk, maybe you want 3 disks in a mirror. Oh.
What's the RAM on the machine, and how did you distribute it in ARC and buffer pool or
Hard cap on the ARC. We can talk more about that later. Because I'm not sure who's coming next, and this is great. I like the questions. I'm just saying that I'm not sure when somebody's going to come in and say, we're done. Am I? No. Well, let's keep going. So hard cap on the ARC. ARC's great, but in database workloads, you want like a floor, or I'm sorry, a ceiling for the ARC, and then give everything else to your application. So in that case, it was like, I think we capped this at 32 or 64 gigs, depending on the workload. We did want some fall through to ARC. And then on the application, single tenant applications, we give something like 25% to the operating system for its metadata and whatever else, minus the 32 gigs or 64 gigs to the ARC cache, and then the remainder of that, minus some fudge factor, would go to shared buffers in the case of Postgres or InnoDB buffer size or something like buffer pool. There we go. I forget. I was just looking at the tunable today and it escaped me. But yeah.
have you tested multiple snapshots and multiple clones and restarted the machine when the system was doing I/O? Because we tried that and the system took a long time to restart.
Okay. Then I will not go into that. But we did, and it worked okay.
So, how long did you put the test before you decided to put in production?
6 months.
Okay.
We beat on it pretty aggressively. We had some pre-production stuff where we tickled a bunch of firmware bugs and had some awful that we had to go and navigate through. And as a result of navigating through that awful, we felt pretty comfortable.
So far, the production server has been running on the test for how long?
Now, I'm no longer at the company where I did a lot of this at a very, very large scale. I'm now at a different company that does this on a very, very large scale. So I can't talk about what I put in production 3 years ago, but I know that it is still in production today, and it is covering 100% of the system, and a single intern is responsible for multiple petabytes worth of database now because the cost of administration is so low, which is amazing, and I'm okay saying that. Okay. They've already taken a copy of my slides. These will be online. Fantastic. Thank you. I'm sorry it was very hurried. I wanted to get to kind of the meat of things, but I wanted to give the quick primer. So.